Okay, so in this video, let's continue. Okay, let's continue. What we did so far, we looked at the uh, amplitude in complex notation of the reflected wave and transmitted wave in terms of the amplitude of incident wave, and it turned out that both of them are functions of the velocities v2, v1. Okay, and now we're gonna look at the actual real part of the amplitudes, okay, because that's what we need to find. Okay, so what is the complex notation in terms of the real time? I can write that for the incident wave, we can write it that a tilde I is AI, and here this AI is without the tilde sign. That means it's a real actual amplitude. It's something you can measure with ruler, okay, something like that, times e to the power of I delta I, and this delta I is the incident wave's wave constant. Okay, so for all three of them we can write it exactly the same. So for the reflected wave, it's a R times e to the power of delta R, and then for transmitted wave, AT is a T e to the power of I delta T. Okay, so we're gonna again assume that we know delta I because this incident wave is coming in, but we don't know delta R and delta T. Okay, so we are quite several unknowns here. Okay, delta I is known, AI is known, but delta R, AR, delta T, AT, technically we have four unknowns here. Okay, now let's rewrite. Okay, let's rewrite this equation in terms of the real values and wave numbers, and let's see what we come up with. Okay, it's going to be interesting actually. So I'm going to draw a line here to separate these. Okay, so from this line down, everything is being written in terms of the real values, and we're going to include the delta wave constants as well. Okay, so AR. Okay, AR, from this top equation, I'm going to say that that's AR real e to the power of I delta R is equal to V2 minus V1 over V2 plus V1 times AI e to the I delta I. Okay, and the second one, the transmitted wave AT e to the power of I delta T is equal to 2V2 over V2 plus V1, and this multiplied by AI e to the power of I delta T. Okay, so now this is a little bit a game of the signs being either positive or negative. Okay, so I'm going to start with this one because this is now a little more trivial. Okay, if you look at these numbers, V is a positive number, V2 plus V1 is positive, AI is positive, AT is positive number as well. Okay, so here we have some positive numbers. Okay, on the left hand side, this positive number times e to the power of e to the I delta T, some other positive number e to the plus I delta T, and if you remember the notation of the geometric demonstration of how we can say e to the power of I delta is like pretty much like this on the real and imaginary frame. So this is this value, this point here. If this is delta, let's say, by the way guys, this is delta I. Okay, so if it's delta I, it's going to be this number. Okay, it has both real and imaginary components. Okay, now if you look at this, you have this positive number, so it's going to be the amplitude, really something like the radius of the circle. Okay, and this shows the direction the same way. This shows the direction. If these two are the same, that means both directions, which are this and these, are the same, and also the magnitudes are the same. Okay, so from this single equation I can say that delta T should be exactly delta I, delta T should be delta I, and also I can write AT, the amplitudes should be the same as well. AT is going to be equal to 2V2 over V2 plus V1. Okay, so let me write it more clearly. Okay, 2v2 over v2 plus, oh, I messed up, this is v1, sorry guys. Okay, so this is transmitted wave and this is multiplied by AI. Okay, and this is good because now we actually, with one single equation, we solve two things. No, in a way, if you want to be really mathematically precise, this is actually two equations because it has directions and amplitudes combined. Okay, but anyways, from this single line, we could come up with delta t being equal to delta I, and that means if the incident wave has any whatever wave constant, the same wave constant will be transferred to the transmission wave. Okay, and this is an equation for the amplitudes of the transmission wave as a function of incident wave. Okay, and these two are always correct. Okay, so we did this one. Now let's go back and look at the first equation. Okay, now here is a little bit of details involved. Okay, so if I want to do exactly the same thing I did here, I can say AR is a positive number, AI is a positive number, but now if we look at this ratio on the top, we have V2 minus V1. Depending on what value of V2 is, and depending on what value of V1 is, it can be positive or negative. Okay, so we can say. So we actually need to make two different cases, and we should say if V2 is bigger than V1, and that is actually exactly equivalent to saying if the second string is lighter, okay, we can come up with something. But if the second, so let me repeat it. If V2 is bigger than V1, means V2, the second string is lighter, this is going to be positive. And if it's the other way around, the first string is lighter and the second string is bigger, heavier, okay, it can be a negative number. Okay, we're going to make two different cases. Okay, so to continue, let me cut it here. Okay, and let me fold it so that we have enough space to continue this. Okay, so we got these two up here, and these are always correct. And here I want to say if, okay, V2 is bigger than V1, meaning that V2 minus V1 is a positive number. Okay, here all these numbers become positive. Okay, I can say that in that case, delta R reflected wave becomes equal to the wave constant of incident wave, delta I. Okay, and the amplitudes, the AR reflected wave amplitude is V2 minus V1 over V2 plus V1 times incident wave. Okay, but if V2 is smaller than V1, that means V2 minus V1 becoming a negative number, then what happens is that the negative, the fact that it's negative, is going to be reflected, make the whole thing negative, and it's going to be reflected in the direction and wave constant here up here. Okay, so then the delta R will have the opposite direction, so that reflects the negativity of this factor in the parentheses. Okay, so delta R becomes delta I plus pi. Okay, and that means reflected wave, it's gonna be out of phase with the incident wave for the pi amount of pi. Okay, so this is gonna be the values, and then for the reflected wave, okay, what we have in terms of the amplitude, I'm going to switch that and make that V1 minus V2 so that this becomes a positive number over V2 plus V1 times AI. By the way, here this should be AI, not I. Okay, so again, I want to repeat what we got so far here. Okay, so the transmission wave and incident wave always have the same wave constants, and this equation is always correct for the amplitude of transmitted wave. If for the reflected wave, then it depends on which side of the string is heavier, which side is lighter. Okay. If the second side is lighter, the reflected wave is going to have the same wave number, the same wave constant, and we have this equation for reflection. If other ways around, then the reflected wave is going to be out of phase, okay, for pi, and then we got a reflected wave equation similar but opposite sign here, so that the both sides become positive. Okay, now what I want to do is that I want to look at two very special cases, okay, and these are important. Okay, I want to look at the first special case is the case that the second string is super heavy, okay, compared to the first string, okay, and we want to see what we get in terms of the equations we have here, okay, and I want to see also what we get in terms of our intuition. Okay, let's first work out our intuition about these waves. Okay, let's say the incident wave is coming in, okay, one single pulse comes in, okay, and now the second string is super heavy, okay, and the way you should think about it is so heavy that the first string cannot even move the second one. Okay, so let's say mu2 is approaching infinity. Okay, so what happens, of course, you can imagine there's not going to be any transmission wave, okay, because this is too heavy to move. And what happens is that whatever we get is going to be a reflected wave. Okay, and now let's look at the equations. Okay, we will be in the regime that V2 is smaller than V1, okay, because this is very heavy. Okay, if you look at this, we're gonna have a reflected wave being out of phase, and if we look at the numbers here, right, in terms of the amplitude of the reflected wave, in terms of the amplitude of the incident wave, I want to write equation as AR equal to, now here we have V1 is the velocity of the wave coming in, okay, V1 is good, but then we got V2, okay, V2 is the speed on this side. If mu2 is going all the way to infinity, V2 becomes 0, okay, so in the numerator we just get V1, and in the denominator again we get V2, which is 0, plus V1, so we get V1 as well, times AI, okay, so this ratio is 1. That means the amplitude of the reflected wave is going to be exactly equal and similar to the amplitude of the incident wave, and that means whatever wave coming in is going to bounce back, okay, and that makes sense. Okay, and if we look at the amplitude of the transmitted wave, okay, AT is going to be equal to 2 times V2, and that's going to be 0 over V1 plus V2, and that's going to be V1 times AI, and this becomes, AT becomes just 0, and makes sense. Okay, so our intuition and our mathematics agree with each other. There's not going to be any transmission, it's going to be reflection, 100% reflection, reflected wave have the same frequency, and that's it. Okay, so this is one special case. Okay, the other special case you can think of is, let's say wave is coming in. Okay, I'm going to draw a second one so that it makes sense. It comes in, and the second string is actually has the mu2 being exactly equal to mu1. Okay, so in fact there's no first or second. Okay, the second is exactly the same as this one, and the wave should not feel any perturbation. Okay, so my intuition says that if the second string is just the first one, okay, and there's no actual perturbation, the incoming wave, the incident wave, V1 is coming in, is just gonna go straight forward and continues. Okay, nothing is gonna get reflected, nothing is gonna change. You're gonna have the same wave on the other side, exactly the same thing. Okay, so this is my intuition. Let's look at the mathematics. Where are we in terms of both of these two? Doesn't really matter, because V1 is equal to V2, and both of whatever route I go, it should work out. Okay, so now let's look at this. Okay, let's first look at the transmission. Okay, so from the top equation, delta t is always equal to delta I. That's good. And the amplitude of transmission AT, okay, is gonna be equal to 2 times V2, which is exactly equal to V1. I'm gonna say 2V1, okay, over V2 plus V1. V2 is equal to V1, so over V1 plus V1. So this is what we get, and times incident wave's amplitude. Now, if we look at this 2V1 over V1 plus V1, this is just 1. So the transmission wave is going to have the same amplitude as the incident wave. So wave comes in, moves on with the same amplitude to the second part. And that makes sense, right? That's what we expected. Now look at the reflected wave, okay? I'm going to get this one and work on this one. V1 minus V2. Okay, what is V1? That's V1. What is V2? That's also V1. Okay, so we get V1 minus V1. And in the denominator, we get V1 plus V1 times amplitude of incident wave. And obviously, this is V1 minus V1 being 0. Okay, so the amplitude of the reflected wave becomes 0. Right, so if you look at this, all the wave transmitted, nothing reflected. Okay, and that matches with our intuition. Okay, so it's always good to look at special cases and look at the cases that you can kind of compare it with your intuition, and it helps you understand what we did, and it also helps confirming, okay, what we did is correct. Okay, so with this video, I'm done with the reflection and transmission. I'm going to stop it, and in the next video, I'm going to discuss the polarization of the waves.